So I messed up and re-recorded over part of the lesson. So the first 21 seconds I forget to start it. So don't think the video's broken. You can fast forward to 21 seconds if you need to. Okay, looking at imaginary roots and algebraic polynomials. Consider the polynomial p of x equals x cubed plus 3x squared plus x minus 5, whose graph is shown below. Looking at the graph, how do we know there is only one real solution? So real solutions come from x-intercepts. So because there's only one x-intercept, we know there's only one real solution. B, is it possible for a cubic polynomial function to have no zeros? So a cubic, degree 3 polynomial. Is there an option for where there's no x-intercepts at all? And there is not, because if you think about a cubic, cubics in behaviors have to disagree. And so because they are in opposite directions, at some point it has to cross the x-axis. Has to. So is it possible for a cubic to have no zeros? No, because of opposite in behavior. This is the reason I chose to explain it. Another way you could explain it is complex roots have to come in pairs. So a cubic has to have three total complex roots, including real and imaginary. But because they come in pairs, that means there could be at most 2 complex roots. So there would have to still be 1 real root. That's another explanation that you could use. C, from the graph, what appears to be the one solution, it appears to be at x equals 1. That's where it crosses the x-axis. So how could we verify that this is a solution? So if 1 is a solution, we could plug in 1 to the equation to get out 0. Or we could do the remainder theorem. That's the way I'm going to do it here. So if I do synthetic division with 1, I should get a remainder of 0. 4, 4, 5, 5, 0. So because the remainder is 0, then that means that 1 is a solution, 1 is a root. So what they did is they plugged in 1 to the equation. 1 cubed plus 3 times 1 squared plus 1 minus 5. And then they showed that p of 1 is 0. That's another option that you have. So E, according to the remainder theorem, what is one factor of the cubic expression? So if 1 is a root, then that means x minus 1 has to be a factor. All right. F, factor out the expression. So we've already done the synthetic on the last page. So let's just show again how we could do that. It would be 1, 3, 1, negative 5. So that gives me 1, 1, 4, 4, 5, 5, 0. And so what that means is the factored form, x minus 1, is the factor that I've already found. And then what's left? My depressed polynomial. 5 is the constant. 4 is the x to the first. And I have 1x squared. So x squared plus 4x plus 5. So I have factored the expression. Now, normally what I do is I try to factor this as well. Well, because the leading coefficient is 1, I can normally do it just by looking. What multiplies to be 5 but combined is 4? Well, it would have to be 5 minus 1 to get a 4. But if I multiplied 5 and negative 1, I would get a negative 5. So I can see here that it's not going to factor. It's not factorable. So the only other way to find the solutions would be to do the quadratic formula. And so that's what we're going to do for G part. So to find the solutions, so again, I know this gives a root at 1. And then to find the other 2 roots, I'm going to use the quadratic formula here. So it's going to be negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So again, let me just simplify that. That's negative 4 plus or minus the square root of 16 minus 20 over 2. And so that's negative 4 plus or minus the square root of negative 4 over 2. And I can see I'm having to take the square root of a negative. That's going to give me my complex roots here. This is negative 4 plus or minus. Because there's a negative under there, that comes out as an I. The square root of 4 is 2 all over 2. And so because everything is even, I can divide everything by 2. So that's negative 2 plus or minus 1I over 1. So my 3 solutions are 1, negative 2 plus I, and negative 2 minus I. And so then on H part, if I need to write an expression with all of the linear factors, so they want this factored out, so that would be x minus 1 times, and so if negative 2 plus I is a root, then that would be, change the sign, so that's a positive 2 minus I, and then negative 2 minus I would be a positive 2 plus I. So here on 2, all they want us to do is write it out in terms of its linear factors. So they want us to practice finding factors. So if I'm factoring, first thing you should always look for, is there a GCF? Here there is a GCF of x. Factor the x out. That's going to leave me x squared plus 5. And now because it has to be linear factors, this is a quadratic factor. So can this factor again? It cannot, at least not in the real numbers. So different ways you could do this. We could go and plug that into the quadratic formula. So that would be negative b, which is negative 0, plus or minus the square root of b squared, that's 0 squared, minus 4 times a times c, all over 2a. And so in all we have left is plus or minus the square root of negative 20 over 2. Okay, so negative 20, that breaks down to be 4 times 5. Square root of 4 is 2, so that's 2 radical 5. But this is also I, right? So 2I radical 5 plus or minus over 2. And because they both have a 2, those cancel. And so that means the other roots are plus or minus I radical 5. So if I need to factor this linearly, that would be the x that was already out front, that was linear. And then I have x plus I radical 5 and x minus I radical 5. And so now then maybe you could do this by spot, just by looking at it and not having to do the quadratic formula. Whenever it's two terms, a binomial, and it's an x squared and just a constant number, it's going to be I radical that number and negative I radical that number are the two factors. 3, we need to factor this. Well, it's already graphed it, which is very nice of them. So what that means is I suspect there to be a factor at 3. Or not a factor, sorry. I expect there to be an x-intercept at 3. So if I do my synthetic division with 3 in the box, it's 3, that's 0, that's 0, that's 4, that's 12, that's 0. So it did factor with a intercept at 3, which means I have a factor at x minus 3, and then what's left over down here, it's an x squared plus 4. And then if I have to make it linear, remember the hack we just saw, little cheat. So this is x minus 3. So from that little hack, that would be, this is going to factor to be x plus the square root of 4, which is 2i, times x minus 2i. Again, if you weren't sure of that, you could use the quadratic formula, or you could actually just solve these. Is another way you could do it. I could set x squared plus 4 but equal to 0. That means x squared must equal negative 4. Take a square root And so x equals plus or minus the square root of negative 4. It's 2i. So again, you could have done that on the previous one too. Just showing you a bunch of different ways. You just need to know one to be able to work these out. 4 says, consider the polynomial p of x equals x to the fourth minus 3x cubed plus 6x squared minus 12x plus 8, and they've graphed it for us. How many zeros does p have? So if you think about that, they've answered it kind of for us. Part 1 of the fundamental theorem of algebra says that this equation will have at least one solution in the complex numbers. How does this align with what we see in the graph to the right? So how many real roots do we see? Well, it looks like it crosses the x-axis twice. So since there are 2 real roots, and it's a degree 4 polynomial, that means we know there's going to be 4 roots total, and I can only see 2 real ones. We expect 2 complex roots, which means it's going to have some imaginary parts. B tells me to identify 1, 0 from the graph. So it looks like it has x-intercepts at 1 and at 2. So if we're just going to pick one of them, let's just say that I have a 0 at x equals 1. It says use polynomial division to factor out the one linear term from the expression. So if 1 is an x-intercept, then we could factor that out. So that's 1, negative 3, 6, negative 12, and 8. So I'm going to use synthetic division here. Bring the 1 down. 1 times 1 is 1. That's negative 2. Negative 2, that's 4. 4, negative 8. Negative 8, 0. So it looks like 1 did work. So that means right now I have it factored to be x minus 1 times, and then what's left? Well, my new depressed polynomial down here is an x cubed minus 2x squared plus 4x minus 8. And it says now that we have a cubic polynomial to factor, we know by part 1 of the fundamental theorem of algebra that a polynomial function will have at least one real 0. So what is that 0 in this case? So normally, to this point, we've had cubic functions. We've done synthetic division once, and then we were able to factor the quadratic or use the quadratic formula because it's just a degree 2 polynomial that's left here. Well, now then, because we started as degree 4, once I do synthetic once, now I have a degree 3 polynomial. So what I need to do is synthetic again on the depressed polynomial to get that down to another linear factor and then the quadratic factor. So because it appears the other real 0 is at 2, we're going to do synthetic again at x equals 2 in E part. So now I'm just going to write down again what I had. So I had x minus 1 times x cubed minus 2x squared plus 4x minus 8. And so now let's do synthetic division here for the polynomial I have left. So I think that the other 0 is at 2, so 2 goes in the box, and then write the coefficients for that polynomial. Bring down the 1. 1 times 2 is 2. That's 0. That's 0. That's 4. 8 and 0. So that worked. So now then, it's factored to be x minus 1. And then what's in red now factors to be x minus 2 times the depressed polynomial here is an x squared and a positive 4. And so we're not done factoring. It'll factor again because we're not down to our linear factors. So x plus 4 will factor to be x plus 2i times x minus 2i. We just had that one earlier, so hopefully you can look back at that. So I've got x minus 1 times x minus 2 times x plus 2i times x minus 2i. Those are the solutions. So now that the polynomial is in factored form, we can quickly see how many solutions there are to the original equation. Yes, we can. There are 4 solutions. They're at 1, they're at 2, and then they are at negative 2i and positive 2i. There are 4 solutions for a degree 4 polynomial. So H says, what if we had started with a polynomial function of degree 8? How many solutions would we expect? We would expect 8 solutions between the reals and complex. Between reals and complex. So if it was degree 8, what would I have to do? Well, if I had a graph that's very nice because I can look, it will give me a few of the possible x-intercepts. And then I'm just going to do synthetic division with those over and over and over until I get down to a quadratic that I can either factor or use a quadratic formula. Sometimes when you get it down, if it started at degree 8, sometimes you could get it down to a degree 4, and that degree 4 polynomial or the degree 3 polynomial will factor by grouping, depending on how many terms there are. So that's always another option you have. But if not, you just have to keep doing synthetic until you get it down to a quadratic. Okay, so what I want you to do now is I want you to do the practice problems. And I'm going to put the answers up in just a second. So go ahead and pause your video here and try it on your own.